In this video, we're going to continue looking at antiderivatives by looking at the initial value problem and how antiderivatives are used in rectilinear motion. Now, dy dx equals f of x is a differential equation because it involves a derivative of an unknown function. Differential equations are different from the kinds of equations we have encountered so far in that the unknown is a function and not a number, such as the equation here, x squared plus 6x minus 7 equals 0. When I solve this equation, I know that I can find a value for x. Now, all the solutions that we have seen so far have a constant of integration c added to the solution. Graphs of these antiderivatives of the function f are called integral curves. And they're all related to each other by vertical translation. So if you recall how I started the antiderivative section, and I asked you to find the derivative of y equals x squared plus 5 or minus 3, we found out that we always got y prime is equal to 2x. So when I found the antiderivative, we knew that it would be x squared plus c, and that c value could be any number. So because it can be any number, that c is actually our vertical translation. So here is the graph of capital F of x equals 1/3 x cubed plus c, and that is the antiderivative of f of x equals x squared. So because it's plus c, c can be any value. So here we have c is 0, we're going to have c is 1, the blue graph, c is 2, which is the green one. We can also have negative c, a negative 1, which is the pink graph, or c is negative 2, which is the orange one. Now, sometimes we want to find a particular solution whose graph passes through a particular point that we're interested in. So for simplicity, instead of using capital F of x, we're going to use y of x. Now, the problem becomes finding a function y of x whose derivative is f of x and whose integral curve passes through the point x naught, y naught. So this is now expressed as dy dx equals f of x, where y of x naught is equal to y naught. And this is often called the initial value problem. Initial value because it's kind of like our beginning or initial value. So in plain words, what we're doing is we're looking for c. Now note that in the James Stewart textbook, that 7th edition that we're using, it uses the f of x notation. So to kind of mimic that and to make it easier for you to transition, I'll also use the f of x notation. So for example, here I have f double prime of x is equal to this equation here. I also know that f of 0 equals 4, but I also know that f of 1 is equal to 1. So I'm going to find the first derivative, and that's going to give me 12x cubed over 3 plus 6x squared over 2 minus 4x, and then plus c. All right, so to simplify, I will have 4x cubed plus 3x squared minus 4x plus c. All right, now remember the initial means I want the original function. So I'm going to say f of x is equal to 4x to the 4 over 4 plus 3x cubed over 3 minus 4x squared over 2 plus cx and then plus d. So simplifying again, I get x to the 4 plus x cubed minus 2x squared plus cx plus d. All right, so now I'm going to use the two pieces of information that I have here to find my c value, my d value. So the first one is f of 0. And when I plug in 0 into this equation here, because remember it says f, so I need to use the one without the derivative notation, I get 0 plus 0 minus 0 plus 0 plus d equals 4, which means that d must equal 4. All right, plugging in f of 1, or 1 for x, I now get 1 to the power 4, 1 to the power 3, minus 2 times 1, plus c times 1, plus d, which I now know is 4, and that should give me 1 when I plug in 1. So here, 1 plus 1 minus 2 is 0. So I have c plus 4 is equal to 1, and c equals negative 3. So therefore, my f of x is equal to x to the power of 4 plus x cubed minus 2x squared minus 3x. And then d is 4, so plus 4. All right, now we're going to do something similar in rectilinear motion. So with rectilinear motion, recall that velocity is the derivative of position. So therefore, position has to be the antiderivative of velocity. Similarly, since acceleration is the derivative of velocity, then velocity has to be the antiderivative of acceleration. All right, so let's take a look at an example. So the acceleration of an object is a of t equals negative 2t meters per second squared. The initial velocity is 5 meters per second, and its position at 1 second is 40 meters. Find an equation to represent the velocity and position of the object. Okay. So starting with our acceleration, it's negative 2 times t. So velocity has to be negative 2t squared over 2. So we add 1 to the exponent and then place that same exponent in the denominator, plus c. So to simplify, I get negative t squared plus c. I can actually plug this value in right now. So I know that the initial velocity, meaning that my time is 0, is equal to 0 plus c, and that velocity is going to be 5. So c should equal 5. So therefore, my velocity function is negative t squared plus 5. And I could have done that above as well. So I could have plugged in the 0 right away, solve for my c, and then plugged it in again later. All right, so now I'm going to find my position. So my position is the antiderivative of my velocity. So I get negative t cubed over 3 plus 5t, and then plus c. So the position at 1 second, it says, is 40 meters. So it's going to be negative 1 over 3 plus 5 times 1 plus c, and that equals 40. So c is equal to 40 minus 5 plus a third. So it's going to be 35 and a third. So therefore, my position function is negative t cubed over 3 plus 5t plus 35 and a third.